Okay, good. Let's try this again. My name is Thore Graepel. I'm chair of machine learning at UCL, and I work as a research scientist at DeepMind. That's a startup company that tries to solve problems in artificial intelligence. This course is a collaboration between UCL and DeepMind to give you the chance to learn about those machine learning techniques that are likely to help get us to artificial intelligence. Here's the overview of what I'm going to cover. We'll talk a little bit about the structure of the course and the team, the people who are offering the course. We have guest lectures given by some excellent guest lecturers, which you will get to know over the course of this module. I'll then talk about DeepMind's approach to AI. I think I would like you to know where we're coming from when we talk about these things, what we want to achieve, and why we think that the particular things covered in this module might help us get to artificial intelligence, or as we try to ambitiously call it, general artificial intelligence. I'll then talk a little bit about deep learning. And I'll then give two very short nuggets of project work. One about learning to play Atari games using deep reinforcement learning, and one about AlphaGo, which is one of my favorite projects. I'll finally have some extra revision material. We restructured the course from last year. Last year, this material was covered in 2 lectures, and I've appended most of the material here. We might not get into that, but if you're interested and want to prepare for the following lectures, you might want to take a look at this material in Moodle. There may be time to highlight a little bit of it. Okay, so let's dive right in. Here's the team that put this course together and will also deliver it. Koray is the head of our deep learning group, and he has sponsored all the deep learning talks and has helped us put this together. My colleague Hado will give the reinforcement learning track of this module, which mostly takes place on Thursday. At the inhumane time of 9 a.m. You may have noticed this in the schedule. That's real self-selection. Anyone going to at that time, I mean, I have the highest appreciation. I certainly won't be there. Well, maybe sometimes. Okay, and then a number of other people played a key role. There's Matteo Hessel and Alex Davies. They are our TensorFlow experts, and they'll give the TensorFlow tutorial on Thursday to give you a good basis for the coursework, which will be coded in TensorFlow, and who've also helped together the coursework assignments. Diana Borsa, can you wave? Who is coordinating the TA support. She's also a research scientist at DeepMind. And Marie, who helps us with the general organization. Marie, where are you? Very good. And also coordinates the recordings. And then we have some amazing teaching assistants. Any of these here? Yeah, can you wave visibly? Okay. Who will help with the coursework assignments. Okay, so that's the team. Let's talk a little bit about the format and the assessment. So we have these 2 streams, and we have a deep learning stream and a reinforcement learning stream. And towards the end, they will thematically converge to some degree. And these are the basic building blocks in what we think is needed to build AI systems based on machine learning. And on Tuesdays, mostly, we'll have guest lectures on deep learning topics. And I'll talk about what that will be a little later. And on Thursdays, Hado will give a structured introduction to reinforcement learning. And also there will be 2 guest lectures at the end of this. So that's roughly the structure, but there are some exceptions, so please check the timetable. We have a schedule posted on Moodle. So one question that sometimes comes up is, how does the assessment of the course work? Last year we had 50-50 coursework assignments and written exam. But we found that it was tricky to formulate really nice questions based on the cutting-edge material that was being presented. And so we thought it would be a better experience for you all if you can just focus on the programming assignments, really work on those deep learning and RL practical problems and learn, rather than having this this exam hanging over your heads. So the idea is basically that we'll have 4 deep learning and 4 reinforcement learning assignments. These will be spread across the weeks here of the module, and then these 8 assignments will be weighted equally, and the final grade will be based on those assignments. These questions will be mixtures of programming assignments and questions of understanding that you will answer in this context. To make things really easy, we decided to put the entire coursework this time into Colab. So Colab is a Jupyter Notebook environment where you don't need to do any setup. This is just connected to the cloud. We can pre-configure it. And we are also providing the computational resources that you'll need to solve the tasks. This is again going back to student feedback from last year, where it was difficult for people to procure enough computational resources to do everything they wanted to do. And so this time we're trying to make design the assignments more carefully, and at the same time provide the computational resources that you need for you in the cloud. We'll use TensorFlow, as mentioned before, and you can find more information about the whole assessment on Moodle. One thing that we needed to do in order to set up these Colab resources is that we whitelisted a bunch of email addresses with the Colab service. And in order to use that, we would like to ask you to create a Gmail account or Google account here with this format, UCL CompGI 22 2018, and the X's represent your student ID. And we've pre-whitelisted those so that if you register this account, you will get access to the Colab service. Also, we thought it would be nice if you have a fresh account for this that you can use. Okay. Then finally, regarding support, we would like to encourage you to use Moodle for all your support queries. If you want to discuss stuff, there's a Moodle forum. Lecturers and teaching assistants will look at these questions and answer them. Ideally, other students can answer them. We want to share the answers to these things. We would like to avoid any one-to-one communication where questions would be answered multiple times, the answers would be shared, and so on. If you have some kind of personal trouble, then feel free to email me with that problem, but please not with any material that could be of interest to others as well. Okay, any questions about the format and the coursework? Get used to asking questions, please. Makes this thing so much more entertaining for everyone, don't you think? Stupid questions are funny, smart questions are useful. Yeah. Yeah, it's just these digits. It's usually 8 digits, and for people who have been at it a little longer, I think it's 7 digits. Yeah, that one. Okay. So just to show you what this Colab looks like. So this is the interface to Colab. You have these cells that you can work with, and you can code directly in Python in these cells. And there's code cells and text cells. So the assignments will come in the form of such a Colab notebook. And there will also be some code available there already that you can plug your own code in to have some kind of unified visualization and plumbing code available. And we hope that that will make the whole programming experience nicer for you. And then we'll ask you to submit this notebook for each one of those assignments together with a PDF printout. It's all detailed on Moodle what exactly is required. And submission, ideally on time. Makes everyone's lives easier and the grades better. Good. And TensorFlow, you probably all know TensorFlow. It's this Google open source software to define and run machine learning algorithms, mostly used for neural networks. That's a pretty standard thing, and I think you'll all benefit from getting exposure to this unless you've already had it. And there are some great jobs out there for people who know how to do TensorFlow. Good. A little warning. This course, we had some feedback on it. It's pretty hard. People were really unhappy last year. Not everyone, but some of them were. So if you do not know how to code in Python, maybe this isn't the right course for you. If you do not have some of the preliminaries required in machine learning, in maths, statistics, and so on, maybe this isn't the right course for you. To think carefully about that. And we created a little self-assessment quiz on Moodle that you can take a look at after the lecture. If you can do the majority of that without problems, then you're in the right course. If you struggle with those questions, then you might struggle with a lot of the lectures, and maybe there's a better course somewhere for you to catch up on those things. Unless you think you have a lot of time on your hands. Who thinks they have a lot of time on their hands? Right. To catch up on some of these issues. Good. Let's look a little bit at the schedule. Yeah, what's your question?
Is it too late for people to cancel courses? Yeah, you have 2 weeks to deregister and pick something else. Oh, really? It is? Oh.
But please do stay if you feel up for it. Okay. So here's a little schedule for the course. You'll also find this on Moodle. You can see here that we have basically these 2 tracks, the Tuesday track on deep learning and the Thursday track on reinforcement learning. And we have some very exciting lectures lined up here on the deep learning track. They are a little bit heterogeneous from the topic perspective because each of these lecturers is an expert in their field. They present cutting-edge stuff leading up to the things that they do in their research. So there's really a gold mine of knowledge to be gained here from these lectures. But of course, you do need to understand the basics very well. And when they go through some of the basics in their particular topic, that will be relatively quickly, so they can go up to the really interesting stuff. On the other hand, the reinforcement learning path is a little bit more structured because this is given by one lecturer, Hado, who also is an expert in his field. And this has more these building blocks that are actually building on top of each other. We think that is also more appropriate because very few people would have had real exposure to reinforcement learning here. And so this is from the ground up. So what you see here on the right are the weeks in which we're aiming to distribute the coursework assignment, deep learning coursework, DLCW 1 to 4, and reinforcement learning coursework 1 to 4. So we're trying to distribute this across the course time as good as we can. Of course, we need some startup time to get going and to get you some of the information that you need. But then we've spaced this fairly evenly to the end of the course. That again is I think an improvement over last year where there were bigger chunks. We hope that these smaller chunks will encourage you to do that work right away, so that you can get the feedback on this work. You can see how what you're doing connects to what you learn in the lectures in a more immediate way than if you wait to the end and then do that work. Okay, do we need a more seat here? Here's one more seat. Do you want to take that? Okay, so let's go through the program in a little more detail because we really have some fantastic speakers, and I'd also give you a little exposure to the topics. So on Thursday, we'll start with this introduction to TensorFlow, which hopefully gives you a foundation for the coursework that you'll be expected to do. It'll be delivered by Matteo Hessel and Alex Davies. And basically, they'll give you an introduction to TensorFlow principles, and then they'll also do some work through examples in Colab, and then later make that Colab available for you to play with. Then, following through with the deep learning track of things, the next lecture will be given by Simon Osindero. And he will cover neural networks, multi-class classification, how backprop works, how automatic differentiation works, how TensorFlow does it for you. So we'll deliver the basics on neural networks in this lecture, and he's a real expert on this. So I'll probably just attend that again because the basics are explained so well. Okay, so then the next lecture will be on convolutional neural networks. Again, we have an expert on the topic. Karen built one of the important neural network architectures that led to a great improvement on ImageNet, on the object classification benchmark. And he's going to talk about convolutional networks applied to large-scale image recognition and show you how these models can be applied to ImageNet as an example, and how the architectures have evolved and how to train those models. The next topic is recurrent nets and sequence generation. So whereas convolutional neural networks assume in some sense that there's a 2D topology, that of an image or some other grid, maybe a Go board. Often we see data in sequence form, for example, text, but other time series as well. And there are specific neural network architectures, recurrent neural networks, that can deal with this. The most successful one that he'll talk about is the LSTM network. And he'll also talk about conditional sequence generation. By the way, he's the person who is driving the StarCraft research at DeepMind. You may have heard that we made available an environment for doing research on StarCraft. Are there any StarCraft players here? Anyone? Yeah. So I think that's a pretty exciting domain. So maybe he'll have some time to talk about that as well. I don't know. We'll have to see. Good. Then Raya will talk about end-to-end and energy-based learning. She'll just discuss some other structures other than just simple regression losses. For example, how to define losses for embeddings, how to define losses when you have relations between 3 data points that you want to embed if you want to do ranking and similar questions. Then the topic of optimization, presented by James Martins. Optimization, of course, is one of the major tools in machine learning. It was actually a major step for machine learning. Nowadays, maybe a few people know this, but machine learning used to be based on rules. You know, people would just define learning rules and hope that the system would then somehow converge to an interesting solution. For example, Cohen maps are an example of where someone just formulated a biologically plausible rule in order to find low-dimensional embeddings of data. And that was always problematic because there were no convergence guarantees and so on. So now, of course, optimization is at the center of machine learning. And this lecture will be dedicated to understanding better what kinds of algorithms are out there and what properties they have, including first-order methods, second-order methods, and very importantly, also stochastic methods for dealing with very large data sets where you might want to subsample examples or take them in very small mini batches. Good. We'll then move on to more advanced topics. Alex Graves will talk about attention and memory models. So the starting point for neural networks were basically these simple feed-forward neural networks. But over time, people have developed more and more sophisticated modules that can do more and more interesting things. And attention and memory are two of these elements. Attention is basically the ability to focus on some subset of your inputs in order to concentrate your processing power on those, ideally where it's particularly interesting. And memory models, in some sense, can be seen as turning that to the inside, when you have some internal memory and you then turn attention while reading it to particular parts of that internal state of yourself as an agent, if you like. And Alex is an expert on this. He developed these ideas of the neural Turing machines, the differentiable neural computers. And in this lecture, he will lead you up to the point where you can understand how these things work. We'll then have a lecture on deep learning for natural language processing given by Ed Greifenstätte. And this is mostly an application lecture, and there's actually an entire series of these lectures because it's quite a rich topic. But these neural language models, neural word embeddings, these things are now the state-of-the-art methods in neural language processing, in natural language processing. And he will explain how these things work and how neural networks can successfully be applied to text. Finally, we'll have a lecture on unsupervised learning and deep generative models. Of course, this, again, is a very complex, big topic, and we could have an entire lecture series on that topic. But we think it's important to give you some exposure to the latest stuff there. Many people think that unsupervised learning is going to be very important going forward, among other things because we just don't have labeled data for all the domains that we would like to look into, but we have vast amounts of data that are unlabeled. If you just think of all the data on YouTube, if we could learn from that, that would be great, right? But we have very poor labeling on that, maybe titles of videos, but that's not really what this is about, right? You want to go into the video stream and learn from that. And so that's a huge topic, very important for AI. Shakir is an expert, and he will explain ideas around this, and in particular also about deep generative models that can actually produce data, for example, image data or text or similar things. Okay, that's, yeah.
You had the integral problem on that slide. Is that what he's working on, or?
Sorry, can you say again? The? Well, I mean, yeah, so if these are latent variables and that's the observation, then this equation, I think he put it there because he thinks that represents basically the deep problem of unsupervised learning. Given these observations Y, to discover these latent causes Z that produce them. And so I think he would argue that in some sense all of unsupervised learning is captured by that equation. Okay, then this is about the other stream, the reinforcement learning stream led by Hado. And he'll talk more about that when he starts lecturing next week. But roughly about the things he's going to talk about: an introduction to reinforcement learning, of course, discussing what Markov decision processes are, which are the underlying framework for doing reinforcement learning. He'll then go into planning and how to do planning using dynamic programming, where there's no learning aspect yet, just planning in a given model. He'll discuss model-free prediction and model-free control. He'll then discuss value function-based methods in contrast to direct policy optimization methods, and how to integrate learning and planning. He'll discuss exploration versus exploitation, which is this problem that comes up for these agents, these reinforcement learning agents that act in the world and have to somehow strike a balance between gathering new information that can help them improve how they can act in that world versus exploiting what they already know in order to gather immediate reward. And then towards the end, for the last 2 lectures, we're planning 2 guest lectures. The first one on AlphaGo, given by David Silver. Have you heard of AlphaGo? Okay, that's good. So I think that will be of interest, and David is a fantastic speaker. I hope we can win him over for this. And the second case study is about practical deep reinforcement learning. Deep reinforcement learning is really this point of convergence where deep learning and reinforcement learning come together because we're using neural networks to represent either policies or value functions for reinforcement learning in a very flexible way by function approximation. And Vladny is the lead author of the paper where this was applied to these 50 Atari games a couple of years ago, 3 years ago now, I suppose. He will tell you the latest about deep reinforcement learning, how it worked with the Atari games, what other domains are out there, what other algorithms are out there, and so on. Okay. Wow, it's a rocket. It's good. So any questions about the plan so far? Plan is clear? Good. So why is there a rocket? Let me see if I can remember. So we're now moving to the part about what DeepMind does and how we approach our mission. And the idea really is of creating DeepMind was to create something like an Apollo program for artificial intelligence. You know, a program where really large numbers of researchers would be focused and would be able to make rapid progress on this problem of AI. And the mission is really crisp, I think. 2 words: solve intelligence. Partly what we're also experimenting with is, in addition to the machine learning stuff, is how to organize science itself. Because it is actually a rather tricky problem to have a large number of scientists and have them work together towards a common goal. And we think we have found good ways to do this, which are somehow at the interface of how it's done in academia and how it is done in startup companies. And in some sense, the idea at DeepMind is to combine the best of 2 worlds in order to really create an environment in which rapid progress towards AI can be made. So the basic premise of our work is that AI can really only be achieved if we can understand how learning works. AI, we think, will be solved by learning algorithms. And this, of course, comes from experience from the past, because in the past, in what we call good old-fashioned AI, other approaches were tried, more rule-based approaches were tried, where people would build systems by combining different rules and bits of knowledge from humans added to knowledge bases or added to the program. And this turned out to be very difficult to scale because these bits of knowledge tend to then interfere with one another. It's also remarkably difficult for us to actually formulate what we know about the problem. AlphaGo is one example of this. Even if you are a Go player, are there any Go players here? It's very tricky to explain why a move is good, isn't it? I mean, you make it, you have this gut feeling, you can come up with some kind of explanation, but it's really hard. And so formalizing by hand knowledge about tasks that we're good at is really tricky. On the other hand, we have learning algorithms, and if we can feed them with examples of what we want to learn, that is a much more powerful approach. But of course, the world is an interactive place, so we will not just have input-output examples for all kinds of problems that need to be solved, and so we need to create algorithms that can go out there into a world, be that a simulated world or the real world, that can interact with that world and find out for themselves what kind of behavior is optimal towards their goal. And so that's the general idea. But there's another thing that we would like to do. We want generality. So in order for a system to be truly intelligent, we think it should be general. It should be applicable to different domains, to a wide range of different domains. And only then would we really be calling it intelligent. If it can only do one thing, then it might not be really that intelligent. And of course, currently, most of the work that we see and most of the successes that we see would qualify more likely as narrow AI that is aimed at solving a particular task rather than a wide class of tasks. And so we want artificial general intelligence, intelligence that can address many different tasks. The important conceptual tool that we use is reinforcement learning. And we really consider this to be a general purpose framework for AI because it encompasses this idea of an agent interacting with the world and learning from their interaction. So the basic setting is that we have this agent and we have an environment and that they interact in these two ways. The agent can observe what's happening in the environment or what the environment is, the state of the environment, and it can then issue actions into that environment in order to change that environment. And the goal of an agent is to maximize long-term reward. Long-term is important here because most of the interesting things that we want to do require maximizing long-term reward. If you want to get from A to B in some city, you don't get immediate reward. You get the reward when you're there, when you arrive, so to speak. So you need to plan long-term in order to get from A to B. And there are many other examples. We can also think of this setup as encompassing supervised and unsupervised learning as special cases because nobody forces the agent to actually submit any actions, and so if you think of this actions block not being there, then we have the environment and the agent is just learning about that environment and getting some kind of reward function according to its goal. Oh, there's actually, this is a little, you can also think of some kind of reward, part of the observations here to be some kind of reward signal that the environment gives to the agent. Yeah?
If you view unsupervised learning as a special case of RL, what are you viewing as the reward?
Yeah, that's a good question, but you could think of some kind of likelihood criterion maybe. That
clear, sort of clearly defined goal in unsupervised.
No, that's right. It's not clear, but I would argue that if you come up with one, then I would be able to put it in this schema. But it's clear that it's, for example, if you wanted to do test likelihood, then there you would have the agent would request examples and would see examples and could build a model internally, and then it would request test examples, and then the environment would issue test examples, and it would get reward based on how well it predicts that. So I think in that sense, it's a very general framework. Of course, it's also a weakness of the framework that it's so general, right? Because it gives less guidance as to how to solve these things. Good. So reinforcement learning, and you'll learn a lot about this from Hado. Since the goal of our research at DeepMind, and maybe the goal of some of you, will be to create intelligence, it's an interesting question to ask, what is intelligence? And our chief scientist, Shane Legg, together with his then PhD supervisor, Max Hutter, came up with this definition here based on mining hundreds of definitions they had found in the literature. It's actually quite an amusing paper to read. So they have a paper where they look at all kinds of definitions from all kinds of sources of what intelligence is, and then try to distill out the main properties that they think should be present there. And here's what they came up with. Intelligence measures an agent's ability to achieve goals in a wide range of environments. Does anyone strongly disagree with this statement?
It's interesting there's no comment on whether the goals are intelligent themselves. Just whatever the goal they've got is.
Yeah, that's interesting, isn't it? Yeah. Yeah, so this in some sense assumes that the goals are given externally, whereas truly intelligent beings maybe generate their own goals to some degree, but then maybe that could be specified as a meta goal from the outside. Yeah, it's a bit tricky. Well, what they try to do here is to be very operational in some sense, and I would like to explain to you how this motivates to large parts the research agenda of DeepMind into intelligence. And that's based on this equation, which I think just looks beautifully. If you squint your eyes, I mean, it's just a beautiful bit of texture here. So let's take a look at this. So they defined this measure of intelligence as a function of a policy pi. You can think of this policy alternatively as an agent that acts in a particular way in an environment, in any environment really. And so the way they define it is through this value function here, which is at the core of it. And this expresses basically how well does this policy or this agent do in this environment mu. So that seems like a good idea. If there is a given environment, then an agent that does well in the environment would be, if there was only that one environment, more intelligent with respect to that environment than an agent that does less well, right? So that seems plausible. Of course, it still depends on how we measure this. But now, this is summed over a set of environments E and weighted. So what this expresses basically is the diversity. We said that intelligence would be required to be successful across a wide range of environments. And so that is the set of environments here. And this factor now here says, hey, but they're not all created equally. Some of them are more important than others. And the way this is formulated here is that this is 2 to the minus the Kolmogorov complexity of the environment. And the idea here is that if the environment is simple, then this term is large and there's a high weight on it. And if the Kolmogorov complexity is large, then this term is low. Now, one advantage of this formulation is that this sum converges, which is always a nice thing for a theoretician, right? You know, if the sum you're talking about isn't infinity. It's a nice thing. But it captures the intuition that there are fewer simple problems, and if you call yourself an intelligent agent, you want to at least score well on those. And then there are more of the complex kind, because they require more description length to specify them. And then if you want to be more intelligent, you need to do better on many of those. Yep.
So is E the set of all possible environments or some set that we define? And also, I mean, we're not really like a human. There's only one big world. So how do you like chunk this into environments? Yeah, it's those are good questions. So as they formulated, this is the set of all computable environments, such that this quantity can be evaluated. But in practice, and that's the important thing for the research agenda, is we define sets of environments. And then we try to do well on them. So we take this as inspiration. We don't actually want to solve this particular thing. It's just, too hard. But the way we view it is, why don't we pick sets of ever more complex
tasks and try to train our agents first on the simpler one and then make that more complex and get them ever more intelligent according to this definition. And so one example that you could take is maybe there's a simple block-based game that you start with, and then you move on to the Atari games, which are visually more complex and have more interesting dynamics, and then you go to 3D games that are yet require more from your agents and so on.
But still, like, for human, there's only one environment, right? And there are multiple tasks, but no one tells you the boundaries between those tasks. So here we're assuming some additional or some different setting, basically, right?
Yeah. If you want to really look at it for the human, it's very difficult, and I think it's an interesting open question how to do this. So in some sense, we interact only through our body with the environment, and where do our rewards even come from? In some sense, they are self-generated through our brain. And then how is that controlled? Well, evolution developed us in some sense, evolved us, and there were certain forces that shaped the anatomy and the chemistry of our brains. And so somehow there never is a reward that can be totally isolated if you look at this complex story. It's just all evolving, and the environment is changing, and you are part of my environment, and I'm part of your environment. And so this is definitely a simplifying model where we're trying to say, suppose there was this nested almost set of environments where they were all well defined. Can we come up with a definition of intelligence within that limited view?
Excuse me. Sorry.
Yeah.
I still don't understand why the negative sign in the power term. So why do we have that negative sign?
Oh, so it's also maybe slightly counterintuitive. The more complex the environment is, the less weight it has.
Yeah, why? I think the more complex the task is, like the more value we should.
Yeah, it's interesting. Yeah, it's these other people have had these concerns as well, and that's definitely interesting. But the idea here is that you should at least nail the simple ones, and then you can move on to the more complex one. But any single more complex one, because there are so many more of them, you in order to really make progress in terms of intelligence, you need to be able to solve many more of those. Yeah, that's the problem. There are exponentially many more of the higher complexity steps. So if we weighted them all even more, this sum wouldn't even converge. But yeah, it's a bit counterintuitive. Maybe it could be captured somewhere in the value that you achieve, that the more complex ones maybe give you more value. For now, let's take it as an inspiration to think about an approach where we have environments on the one hand side that we can construct, and we have learning agents that we can put into these environments and train. And we basically want to cover our bases and be able to have these agents be successful in the simple ones. And then we want to ramp up the complexity of these environments and be able to solve ever more complex ones. You can also think of it as a curriculum if you do it in that order. Of course, there's no order implied here, but I would recommend starting with the simple ones and then moving on to the more complex ones, as humans often do during their lifetime as well.
I'm surprised there's no penalty term on the size of pi, because you could think that you should be intelligent per for a given age or for a given complexity of policies.
Yes, that's also interesting. You might have it in the V, right? For example, if a complex policy was encoded through a complex neural network, which would require a lot of energy to evaluate, then if your task was to come out of the environment with your maximum amount of energy, or survive as long as you can in the environment, then you could code that all in the actual environment and reward combination. And a smaller neural network would then be advantageous because it's actually better at the task, because the task involves resources and it's better at preserving resources. Okay, but you see, you can get into a lot of discussions even at the point where you're trying to say what you want to solve. So tricky questions. Okay, so if we think about our own intelligence, then certainly it didn't evolve in a purely abstract world. It is grounded in rich sensory motor reality. We see things, we can manipulate things, and we know that, for example, babies learn in this way. And to get some of this, people have looked at games, video games, as a particular set of tasks that are really nice for this purpose. And a lot of the work that we do, as you know, Atari games, AlphaGo, is based on games. And I personally think they're a fantastic platform for AI algorithms. So what are the advantages? These are basically simulators, right, the game. So you have unlimited training data. Anyone doing machine learning surely appreciates that. Of course, it comes at a cost. When you run the environment, it also costs you resources. So there's a trade-off in some sense. You need less data, but you need computational resources. We can run these in simulation, and that has a lot of advantages because we can have many instances, for example. In training, we can have thousands of computers run the same thing and train, and that's very powerful. If you compare that to a robot arm, that is much trickier because then you have to deal with the mechanics of the arm. You need physical space to put the arms. You need to maintain them. They might change over time and so on. So working in simulation is really attractive. And so a lot of the work that we do is in simulation. Now, of course, the disadvantage is that it's not the real world. So we might be missing out on some aspects of the real world, like measurement noise, changes in the dynamics, stuff breaking, the real world. But the idea here is we can make progress maybe first in these more abstract games domains, and then we can move to the real world later. So the goal in these domains then is to do end-to-end learning agents. And basically, we want to formulate an algorithm that observes the world in some sense, issues actions in interaction with the environment, and learns how to solve the task without further input from humans. And that's how the Atari work came about. And I'll talk a little bit about it later. But that's basically the research philosophy that we're trying to follow at DeepMind, and which we think is a promising way towards developing artificial intelligence. Good. Let me just see the timing. Shall we make a 10-minute break maybe, and then meet back here 3:05? All right, thanks. We just did some online learning here and found out that our instructions don't quite work the way we intended them to. Hold off with the creation of those Gmail accounts. We'll need to figure out what exact characters Gmail addresses can contain. Apparently, dashes are not among them. So we'll update that on the assessment part of the Moodle page, so you can take a look. Also, just to clarify, these coursework bits are individual pieces. They are not to be solved in teams, if you know what I mean. Of course, it's always nice to advise other students and help them in some way, but do it in very general terms. Okay, let's talk a little bit about deep learning. Deep learning is a hot topic. When we think about it in the context of artificial intelligence, we think of it as helping us solve this perception problem that we want our agents to be able to comprehend the world, to perceive the world and then comprehend it, but to perceive it at the level of the sensors by which they perceive it. So for video or images on the pixel level, the raw data. And while this sounds maybe very natural to you now, again, this wasn't exactly the agenda of AI in the past, which often worked at a symbolic level, and where problems arose because it was very hard to connect that symbolic level on which certain manipulations were relatively easy with the actual underlying sensory motor reality. Because you might have some idea of maybe how to build a tower or something out of pieces, but if you just direct the camera at the seed, you first need to figure out what are the pieces and how can I move them. So a purely symbolic solution is kind of hovering somewhere abstractly and is disconnected both from what you can see in the world, because it's hard to get that symbolic representation from pixels, and to get it back into the world. Once you've drawn some conclusions, you want to act in that world. And so we want that connection. And it turns out that deep learning offers very nice tools for this, because it is currently the framework that is most successful in processing, classifying, and so on, perceptual stimuli from those raw sources, like audio or images or videos. So, what characterizes deep learning? One big thing is that it is based on end-to-end training. So we want to formulate a model and then train it end-to-end. Say we have labels and images, and we just want the system to be optimized end-to-end for this problem. We don't want to engineer features, because that would require human input for every new problem. We want these features to be automatically learned. We want the system to learn good representations. And neural networks have come back, so to speak, to be able to do all of these things, and are now very versatile, can be applied to images, to text, to audio, to video, to go positions, whatever you like. These systems are modular in design. So because we do gradient-based learning, we can stick together modules and pass the gradients through these modules and learn the parameters of the individual pieces. It's not that they don't have any prior knowledge built in. There are a lot of different architectures, and every architecture of a neural network gives the system some kind of inductive bias or represents some form of prior knowledge. The most well-known one maybe are convolutions. Convolutional neural networks encode certain spatial relationships in the inputs and facilitate through that specific weight sharing the processing of images, which, for example, often have translational invariance or localized features. The way deep learning has come about is it evolved from normal neural networks, but it was then enabled by having more data and more compute power, in particular GPUs, of course. So if we look at what's out there, and we'll have more lectures on the details, of course, but I want to give you a little sneak preview. The convolutional networks pioneered by Yann LeCun and others are the basic idea for processing images and making use of these biases that I was talking about, and were successfully used for classifying digits and handwriting on postal codes on envelopes in the US Postal Service. And of course, this is a comparatively small problem, but then the real breakthrough was that they could also be applied to this huge data set of ImageNet. ImageNet is a good example for how you can make a great research contribution, not just by creating new algorithms or delivering new solutions, but also by posing new problems. So ImageNet is this huge data set which has 1,000 different classes of objects. And for each of these 1,000 different types of objects, there are 1,000 example images of those objects. And this data set alone has really boosted research in image recognition, and in particular in deep learning. So if you're ever in a position to curate a really big data set, it can be a beautiful contribution to science to do that. And in 2012, there was this big breakthrough of really reducing the error rate with large convolutional neural networks on this ImageNet data set, bringing it a lot closer to human performance. Now human performance has been surpassed on that. And that was really the kick-off point for the modern era of deep learning, if you like. These convolutional neural networks can also be applied to text. It's an interesting question why that might be the case. Well, text is also on some kind of grid. It's just a one-dimensional grid. It's a sequence of characters instead of being a two-dimensional grid of images. And again, we can use the same kind of prior knowledge, namely that we would like to have localized filters that can find local features in the text. And this was applied both at word level, but more interestingly also at character level. And we can also we also have the shift invariance that we have in images. You know, if there's a particular combination of characters here that have a particular meaning, for example, or indicate a particular class, then if that is shifted somewhere else in the text, it might have a very similar meaning. So those same ideas apply to text, and hence convolutional ideas can be applied here as well. And then, of course, you can go one step further from images, going to stacks of images, if you like, to videos. And again, convolutional neural networks have been very successful here. The author of this particular work is Karen Simonian, who will give the lectures on convolutional neural networks. So you'll be able to learn much more there. What's essentially happening is that you learn one big nonlinear function, and I would like to point you particularly to this idea of viewing deep learning as differentiable programming. I think that's a very powerful idea. You have to imagine 20 years ago nobody did neural networks. So 30 years ago, and then again maybe 15 years ago, people had these simple feed-forward neural networks to approximate functions from input vectors to output vectors. And they had usually very uniform architecture, just fully connected layers one after another, trying to approximate a given function. What happens now is that people define these modules and stick them together. You can have convolutional modules, you can have memory modules, you can have attentional modules, you can have fully connected modules, you can have output modules with softmax and so on. You stick together these building blocks and you really program in this space of models. And of course, you leave degrees of freedom free, namely the weights, the parameters within these models, and they can then be learned end to end by propagating errors through this system. And so I think that's a viewpoint that is very useful, to really think of it as a new programming paradigm where we leave a lot of the program unspecified. Those are the weights that need to be learned, but we do encode the structure that we know into the neural network. Recurrence, of course, is also an element of that, if you have a recurrent neural network. So in terms of architectures, you can see that people have gone wild and have developed different things, starting from these humble beginnings. In the inception network, the topology was varied. You see these, they're not just stacked linearly in one direction, but you see there's different paths through this network. So there's almost like a 2D structure to it. In ladder networks, it's an unsupervised type of system where you have horizontal connections between layers that facilitate learning locally within each layer, because every layer doesn't have to wait till the output, and then again the input is reached through the propagation. There's ResNets, which have this idea that there's always two paths through a layer. There's an identity function that kind of skips the layer, but there's also a nonlinear function that can then is then used to fit the residual. Everything that just stays the same can be sent through the identity, and then this bit can fit the residual, and those are stacked on top of each other. So people have really explored various architectures and have improved on the metrics, for example, on ImageNet. This particular thing came out of Microsoft Research in 2015, the ResNet, and made a big jump in the performance numbers for ImageNet. But you see how this resembles programming, putting together these architectures. And of course, a framework like TensorFlow is exactly designed to do that, to stick together elements and then leave the actual implementation of the propagation of errors and gradients to the system. Okay, similarly in unsupervised learning, there was a proliferation of architectures and models, restricted Boltzmann machines, autoencoders, things that do PCA and ICA and sparse coding, sometimes stacking layers of these on top of each other to achieve hierarchy. And of course, a recent favorite are also GANs, which are a beautiful idea in that they take this single player problem, if you like, of matching, of finding a density model, a generative model. They turn that into a two-player game where there's one agent, if you like, that tries to produce examples that look a lot like what you want to produce, and the other agent needs to judge if that looks right or not, and needs to distinguish those artificial examples from those given in the training set. Beautiful work. So a lot of stuff, and we'll learn more as the lectures continue. Then, of course, sequence modeling, incredibly powerful. The example that I like the most is how you can formulate the simple task of translation as a sequence transduction problem. It's just beautiful to view it that way. You have an input sequence, which is your text in one language. You have an output sequence, which is your text in another language. And you really view translation just as a mapping from one sequence into another. And at first, that's beautiful, but people thought it didn't work. And then they found that you can actually make this to work. And now most translation systems are based on these types of networks. Incredibly powerful, and also working at this symbolic level of characters and words and so on. And Oriol Vinyals, who's also responsible for a lot of the progress in this area, will give the lecture on sequence modeling. Okay, that's the deep learning overview. And now I'll move on to these two little bits of research to give you some idea of what can be done if you combine reinforcement learning ideas with deep learning ideas. And we'll start off with the work on human level control through deep reinforcement learning, the work known as the Atari work, if you like. Which was one of the first big papers that came out of DeepMind. And I think you probably have all seen these Atari games. I think just discovering that this kind of problem exists was a huge step. And it was people in Alberta first came up with the idea, can we use a collection of these simple Atari games that children play, that grown-ups play, admittedly, and that can be quite addictive and interesting. Can we turn those into a reinforcement learning challenge? And what's so beautiful about them is that they offer a rich visual domain. You know, this is just one of them, Breakout. But of course, there are a few dozen others. And what they have in common is the action space and the observation space. So they are really, if we can call them a family of problems, because when we observe the state of the system, we see an array of pixels or stream of images. And that's the same for all of these games. The content of those images, of course, is different. The way we need to interpret them for each game is different, but the format is unified. The same holds true pretty much for the action space. Imagine a controller, a joystick. You can enumerate the actions that you can make on this, and so we also have a unified action interface. And so we can really view this as a unified family of problems. We have many different games, and that, going back to the definition of intelligence, gives us the ability to train a system that can do many different things and can be tested on many different scenarios. Now, how do we know these are interesting problems? They could be super boring problems. But no, humans designed them to be interesting for humans. So we know they're interesting, right? They're interesting in exactly the sense that we're interested in here, because they're challenging for humans. They become more difficult as you progress. They involve manipulation. You need to do the right kind of combination of moves, and so on. You need to understand conceptually and so what's going on the screen. And yeah, it's a tough problem. Let me just see. And again here, by the way, finding the right problem is such a key skill, right? If you can come up with a nice problem that is close to solving, then you're in a beautiful situation. Okay, so putting this back in the context that we had of the little reinforcement learning diagram, we can think of the game as the environment, and what we want to build now is the agent, the controller. And the agent will take in observations from the environment, which are these images. In fact, what they do is they take, they concatenate 4 of those images because they want a little bit of history, so to speak, of what the past looks like. To see, for example, in which direction the ball is flying, you need a little bit of a trajectory. And then they create this Q network, which takes as input those images and outputs for a given state for every available action the so-called Q value. And we'll learn more about that in the reinforcement learning lectures. But the Q value basically indicates for each state how good it would be to execute one of the available actions in that state. And then, of course, you would want to pick the one that maximizes that Q value. And the sense in which this move or this action will be good is in the sense of long-term reward, because the Q function will represent the long-term estimate of how much reward you will get if you execute that action in that particular state. So, and then you can imagine this the training happens through the interaction with this environment. And the results across these 50 domains, 49 I think, were quite stunning in that for many of these games the system reached human level or superhuman level performance. There are also a few games for which that wasn't the case. And you can imagine what the distinction is. If you have a more reactive game where everything you need to know is currently on the screen and you need to react immediately to what's happening, that's relatively easy. There's also a more direct feedback signal there because, for example, in Pong, if the ball goes by, you might get a negative reward. So those are relatively easy. What is hard is if you have more of a puzzle game. There's a game called Montezuma's Revenge, I think it's called. Is that right? Yeah. You know what that means in Mexico, right? game is basically more like a puzzle game where there's a very narrow channel of actions that you need to take. You know, there's something you need to jump over, and then you must not fall into the thing, but avoid something, and so on. And so that is very hard, because the reward for doing all that only comes much later, when you have collected a key and then gone with that key later on through some door. And then you get a positive reward. And so that is very hard, because the reward is very sparse and very long term. And so that's much harder to do. And so, but for a lot of these games, that algorithm was successful. You'll learn more about it from Vlad. But it is really quite nice to see. Oops. How in this particular game, the controller has learned to shoot the fish. If it collides with the fish, then it loses a life. And what you see here is the value function, and here is the Q value for each of the actions that it could take: up, down, left, right, firing, and so on. And here is the so-called advantage function in time, which is basically the advantage each of the actions has over the others. Technically, is the Q value minus Q function minus the state value function. And it uses basically this and takes the action that maximizes this here. And what's interesting here is shooting the fish is relatively easy, and it survives for a while. Early models of the algorithm didn't find out that once your oxygen level is very low, you need to go to the surface to breathe, to survive. But then as research advanced and the training was able to capture more long-term relationships, the algorithms also figured out that that's what it needs to do. So short-term, shoot the fish, evade the fish, but at some point when this bar is low, go to the surface, get oxygen, then go back down. Just to point out how hard this is, because it's not maybe immediately obvious. And the system just gets this image here, and it doesn't know what it controls. So it doesn't know that it is the submarine. Right? It has no idea about that. It needs to find out that it needs to control this. Of course, we have no idea how it represents that, but somehow that's the task, right? When we approach this game, we wiggle the controller and then we see, oh, I'm this thing. And then we have all kinds of semantics. You know, we know that we observe a collision with a fish, and then we know, oh, colliding with fish isn't good. Oh, I can shoot. And oh, oxygen is probably up there and not down there. You know, all of this prior knowledge we bring to this problem. And that's why humans, of course, also learn these games much faster than computers currently do. But it is remarkable that computers can learn it at all, I think. Brother, you had it first.
Just roughly how much interaction to get to this level?
I think millions of frames. Yeah.
You mentioned when the reward gets too long term, the algorithm stops working. Is there some sort of theoretical limit, like once the number gets too large, like you go or something?
Yeah, so the problem is in order for these problems to be formulated mathematically, you need to decay the reward. So either you have a finite sequence, and you just add up all the rewards. But what we typically do here is we have some kind of discount factor. And so we say that further away rewards count less than more nearby rewards, you know, a bit like interest rate. And that decay factor pretty much determines how far we take into account those rewards. But the problem is that you might not even see them. So you don't get to train on a perfect trajectory where at the end you get to see that reward. If you make the wrong moves and die before, you never see it. So it's also related to the exploration exploitation problem, that you are the agent itself is the data generator. So if it never manages to even see a reward because it dies beforehand or the episode ends in some way, then it will never get that reward. And maybe every now and then, because it still has randomness in there, it stumbles upon the reward, but then that reward is very rare. So the problem with the long-term reward is both that it's hard to propagate it back, but also when it requires complex trajectories to get there, you might never see it because you never get there.
So human-level planning, that doesn't get captured in the algorithm at all?
There is some degree of planning. So when you see a reward, it is propagated through the Q function backwards in time. But we do much more, I think. We also get intermediate rewards just by, seeing, oh, I moved to the right and it moved to the right. Yeah, you get that kind of satisfaction. Or you shoot a fish and it disappears and you get that kind of satisfaction. Here there are actually some rewards for shooting fish, so it depends on the definition of the game. But the very hardest games have almost no intermediate reward, and you only get it at the end, and those are the tough ones.
Is there any knowledge transfer across tasks? Like, is it easier to learn a new game?
Yeah, so that's a very good question, and I need to clarify something that is maybe not clear here. So what happens here across these 50 games is that the system is trained on each one of them with the same hyperparameters and so on, and then tested on that same game. And the system is universal in the sense that you can apply it to each of those 49 games and test it on it, and it produces respectable results on all of them. There is not a single system here that can play more than one game. But in the meantime, people have worked on this, and they have created systems that can play several of these games. But it's very tricky because suppose you want to learn them in order. You first learn one game, but now when you learn the second game, the learning updates for that game destroy what you have learned for the first one if you apply it to the same neural network. And so you either need to mix the tasks so that you never forget the old one while adding information to the new one, or you need to somehow protect the weights that were learned for the first game while learning the second, and then protect the ones of the first and second game while learning the third. And these are very tricky questions. It's called lifelong learning. And that's just protecting those weights. What you are referring to goes even further. What you would like to see is that you learn the first game and you've now learned certain concepts like moving left, moving right, up, down, objects. And now it should be faster to learn the second one because now you've already got some prior knowledge from the first one. And that is an even harder problem. You want to transfer information from one domain to the next. But that's the holy grail, really. That would be ideal if the system learned at a level of conceptualization, so to speak, that the things it learned in the first game would be useful for learning the second. These systems don't learn at that level. They learn more at the pixel level, and they never have this notion, for example, of an object. For example, one of the key things that you would really want to learn about these things is that there's this blob somewhere, and you're it. And when you move your joystick to the left, it goes to the left. And when you move it to the right, it goes to the right. Those things, we currently have no way of learning that. But that's certainly the future. We need to learn at that level of generality. It's a great question. Yeah, there?
How much do you have to tell it what are the rewards and punishments?
So what it gets is, with each observation, it also gets rewards. And for example, if it just shot a fish, then it will get a little number, and it'll interpret that number as the reward. And when it dies, it gets a negative reward, or it stops getting rewards. That's really all it gets, but it uses the sum over those numbers weighted by that decay factor as the optimization criterion for its learning.
So are those numbers predefined for each game?
Yeah, so they are they are here derived from the score. It's another advantage of this test suite, because the game designers, in some sense, already provided the reward system. It's the game score. And there are some problems associated with it, because for each of these games, those numbers can have vastly different numerical quantities. And so the system needs to be robust to that. And they use reward clipping, for example, or rescaling of the rewards to make sure that they are all roughly in the same order of magnitude.
So, for example, in this example, have you explicitly stated, sort of told the model that the score is its reward, or does it?
Yeah. So there is a system called ALE, Atari Learning Environment, that explicitly translates these games into a reinforcement learning environment and interprets the scores that it finds as a reward and segments those out. Yeah. Okay. Now, in some sense, we're here in the very early stages of, the simpler environments, and many people have now moved on, although we're still using some of these environments to test algorithms that we develop. But here's a newer generation kind of set of environments called DeepMind Lab, and this is also publicly available and constitutes a kind of first-person perspective of some maze world where different tasks can be represented. What's nice here is all of these tasks play out in some kind of maze, and the agents are in there with a first-person perspective and see the world from this first-person perspective and move in the same way. So again, we have a family of problems that have a unified input-output interface. They always see the pixels that come in, and the actions they take are turning, moving forward, moving backward, maybe shooting, I'm not sure. And now various different tasks can be formulated within this environment, and agents can be trained. Here's basically such an agent, and when it interacts with that world, it gets the first-person image of its position in the world, and it gets some kind of reward depending on what it encounters in that world. And here are the action spaces. Can basically go forward, backward, turn, strafe, jump up, and that's it. Unified for all tasks within this task suite. And now you can see that this is a much more demanding kind of environment. Here's someone navigating it. Apples in this case give positive rewards. And you see the difficulty here is to interpret this 2D image in terms of its 3D, what it represents in 3D, and learn how to navigate the maze based on certain things. For example, you see here there's images on the wall. So in principle, once the agent has navigated the maze for a while, it could have built up some kind of map knowledge of the situation. And if it finds itself in a spot, then it might orient itself by recognizing that there's a particular image on the wall, and then it might draw conclusions about what its best course of action would be in that particular situation. And there's all kinds of interesting tasks that you can do here. Maybe mostly tasks related to navigation, because you would, find the apple or walk through the maze and try to collect as many apples as possible. Things like that you can do. But you can also do other things. For example, this is a kind of laser tag level in space where the mode of movement is a little more complex. You have these ramps where you can fly through space and get from one platform to the other. And again, put yourself in the position of an agent seeing this and having to learn what it means, what it sees. It sees a 2D projection of a 3D world from a first-person perspective, and somehow needs to derive from that what actions it would be advantageous to take in that particular situation. Okay, so much for that, and I think Vlad will be able to give you much more insight into this and how to address these types of problems, different algorithms, and so on. As the last point for today, I'll talk a little bit about the AlphaGo project to give you some inspiration for some more application of deep learning and reinforcement learning. I saw that we have at least one Go player here. I'm so glad. Strange though, aren't there? See, we have 2 Go players. You could play. Maybe you are playing and I'm just not seeing it. Okay, so Go is a very different type of problem. So the problems we just looked at in this labyrinth are very much inspired by how we see the world and interaction with the world that is naturally spatial, where an agent has a given position in that space, moves that position around, has a perspective that is tied to that particular point. Of course, Go is a problem that is difficult in other ways. It's played on this board, as you know, 19 by 19 with black and white stones. There's no agent that you are in this game. You place stones on the board. In some sense, the stones may be the agents, but they're not actually doing anything. So the player is the agent, but it's not so clear what the player's representation is, other through which stones they currently have on the board. And the goal, of course, is to surround territory in this game. And here the challenge is quite different, because here we have a super large search space, a huge search space, in fact, represented by this the game tree, which has a game tree complexity of the breadth to the power of the depth of this tree. So the breadth is how many different moves you can choose at any point in time, and the depth is how deeply you have to look down in the tree. And the other problem, of course, that needed to be addressed here is one that it turns out deep learning was suitable for, namely to assess how good a given position is, to evaluate a position. And if you look at the problem, it's kind of natural that you would think that that might be the case, because it looks a lot like a vision problem. You know, you look at the board, it has a 2D structure, like a grid structure, like an image. And so we know humans are good at it, or can be good at it. Very few humans are actually good at it. But there are some humans who are good at looking at the board and determining, for example, if black has the advantage or white has the advantage, or what would be a good move in a given situation. And that's where deep learning comes in. Now, here's an illustration of chess, where you have maybe roughly 20 moves in every given position to consider, which is already a lot. And of course, in Go, it's many more. It's up to 300 moves, really. So how is it done? We use deep learning. And we have 2 types of networks here. One looks at the board and finds a mapping from a board position to an evaluation. So it's basically trying to estimate how likely it is that black or white would win in a given situation from looking at the board. And the other network is the so-called policy network, which looks at the board and looks at what might be good moves in this particular situation. And both of them are visual tasks that humans can do. We know that a good Go player can look at the board and maybe at a glance see who is in a better position. Sometimes it takes more analysis to do it. But what Go players definitely can do is look at the board and see plausible moves. Or maybe they do the contrary. They say they see a lot of moves that definitely aren't good and they're not going to consider. So they select which moves they are going to analyze more precisely. And those, of course, correspond to particular visual patterns that are not unlike the visual patterns that we pick up when we do object recognition or when we recognize faces. There are combinations of edges and areas and, connected bits and pieces. And so it's not that surprising that a convolutional architecture can actually represent this mapping. I still find it somewhat surprising, because if you change a single pixel in an image, that never changes the semantics of the image, right? There's almost no way it could do that. Whereas if you change a single stone on a Go board, it might very well turn it from a winning position into a losing position. And so there is something specific about this mapping problem. It's not as smooth as maybe you would think of the typical visual recognition problems. Well, how is this used then? And you can basically think of the planning process here as being represented by a huge game tree. And the problem of it is the game tree is too big. We cannot search it, but we can reduce it in 2 dimensions. By using the value network, we can avoid having to evaluate all the way to the end when we know the outcome of the game, but we can evaluate earlier. And by reducing, by selectively only looking at moves that look promising, we can make the game tree much more narrow, and in that sense, again, reduce the size of the tree. And the remaining tree, if you like, then is amenable to search techniques that can get us good results.
Do you end up using, at that point of paring down your tree, is it Deep Blue-like exhaustive search?
It's called Monte Carlo tree search, and so it's still a little different. Monte Carlo tree search always picks one trajectory through the tree, and always develops a new node at the end and grows the tree in this way. So it's different from what Deep Blue would be using, which is a min-max search, using a heuristic called alpha-beta pruning, where it basically can disregard certain parts of the tree for logical reasons, but otherwise has to expand large portions of the tree. So the Monte Carlo tree search does more of an averaging. So in min-max search, you really assume that you have an accurate evaluation function, and one player tries to maximize it and the other player tries to minimize it. Whereas in Monte Carlo tree search, we average the evaluations. We just make sure that we only ever go down promising routes in the tree enough times that the averaging is biased towards maximizing and minimizing. It's a nice, robust search technique. And then, as you probably know, this AlphaGo turned out to be much better than the existing programs at the time, which were only at strong amateur level, whereas AlphaGo, the early version, went into professional territory and eventually beat the strongest player in the world at this game. And the evaluation was first against Van Hooy, the European champion, and then later against Lee Sedol, the Korean champion. Yeah?
If you reduce the board size from 19 by 19 to a smaller size, does it become tractable brute force?
Yeah, it becomes more tractable. But you have to go to 7 by 7, I think, for it to be really tractable. 9 by 9 is still difficult, and 11 by 11 is about as complex as chess. So, but there's an interesting idea there. We talked about these ever more complex environments in the definition of intelligence, and one way to formulate a curriculum over this task, for example, would be to start learning on smaller boards and hoping that you can have an architecture that also works on bigger boards. And by learning on smaller boards first, you would have first successes and a smaller space, and you could learn some basic patterns that would then transfer to the larger boards. And I think that could be a promising route to address that.
Checkers has been brute force solved, and it's about 500 billion positions.
Yeah, that is very interesting. Yeah, it's a smaller game. It definitely is a smaller game, but it's people have made progress. They go from the end game positions backwards, and from the openings forwards, and then at some point they match and can prove a result. Okay, and of course there's more here, and we'll hope to that Dave will cover this in his guest lecture. Of course, recently we've made a lot of progress, whereas in this earlier work we used supervised learning to train these neural networks. We used games that were actually played by humans and used them as supervised learning data sets, taking a position and a move as a classification problem. Position is the input, move is the class, if you like, and we were able to train these networks. But more recently in the AlphaGo Zero work, we can do this entirely through reinforcement learning, where the system only plays against itself and learn how to play Go even better than with human input, strangely. And then we also applied that to chess, but that's really just a preview to Dave's lecture. Okay, final thing, I would like to point you to some extra revision material. This was last year included in the second lecture, which we've now replaced by the TensorFlow tutorial because we thought that was better use of the time. But if you want to take a look just at the slides that we posted on Moodle, there's some basic revision of regularization, generalization in supervised learning, and how gradient-based learning works in linear regression and in logistic regression, which are the models that kind of lead up to feed-forward neural networks then. Okay, any questions?
Will the recordings be available on Moodle or otherwise?
We're still trying to figure that out. There's a lecturecast recording and there's these recordings, but so far we haven't been able to combine them onto a Moodle, so have to find out.
This is quite a broad question, I guess, but when you train the AlphaGo Zero and the Chess Zero programs, and they're obviously very good, but do they play like a human? Do they play like an even better version of a very good human? Or are they doing things that, I mean, I don't know if I'm phrasing it.
Yeah, no, I see what you mean. I mean, we were very interested in this question ourselves, because in some sense you can view these games as illustrations of maybe what happens as we make AI stronger and stronger. So here we have small worlds, and we're now at a point where the competence of the AI is greater than the competence of humans in this particular domain. And so what does that look like? What is it like to play against a higher intelligence, so to speak? And maybe we can draw conclusions that would also hold for other domains that are maybe even more useful, like medical diagnosis or car driving or whatever. And so we were looking at this, and some of the moves that AlphaGo made, even during the first match in Korea, were pretty amazing according to our experts. So they were truly surprising. People were using the word creative moves, inventive moves, because some of the moves defied well-established rules that human players typically respect in their game. Humans have a lot of heuristics that they use to select moves because the game is so complex. But what that also means is that they have certain biases that are very hard for them to overcome. So if they have, for example, a trained pattern that tells them that a particular move cannot possibly be good, but in this particular situation, that move happens to be the best move, then a lot of humans would have difficulties finding that move because early on in their reasoning, they would rule it out. But AlphaGo didn't have those limitations, or not to that degree at least. And so it came up with moves that were counterintuitive to humans, but when they then saw how the game unfolds, they suddenly realized how brilliant that move early on was, that they previously didn't understand based just on their rules. So that was pretty amazing to see. And then more recently, we had some interesting feedback on the chess games that we published, where we applied this same methodology to chess. And some of the grandmasters were amazed at how flexibly AlphaZero evaluates positions. So when you normally write a chess program, you would define an evaluation function that tells you how good a given position is. And that would include the material, do you have more material than your opponent, queen, king, pawns, and so on. It would include pawn structure, king safety, mobility of your pieces, and so on. But they would all have some kind of fixed coefficient. that the programmer would have to put in so that you can actually evaluate this function and do a search based on it. Now, the AlphaZero approach doesn't have any of those limitations. It just learned this general function from board state to evaluation. And as a consequence, it's not bound, for example, to the concept of material. So it much more easily satisfies a piece in order to gain positional advantage if it has learned that, in fact, that increases its winning probability. And so in some of the games that we shared, AlphaZero plays a sacrifice which is a positional sacrifice. It loses the piece, and almost no human player would do that unless they knew exactly what they were getting for it. But AlphaZero was happy with that move increasing its winning probability, and then somehow 40 moves later it would get that home and actually win the game. And so that was pretty otherworldly in terms of playing style, and chess masters just enjoyed those games a lot. Yep.
I heard that at least when the first Nature paper came out about AlphaGo, that it was open source. Is that possible for someone else to recreate?
No, it wasn't open sourced, but there are other programs, other groups that have in fact started reproducing this. I think there's an open source project called Lila, Open Lila or something, Lila Zero, which is trying this. And there's also Tencent, the Chinese internet company, has a program called Fine Art, which is designed according to the AlphaGo specs and has become much better in recent times, and is also challenging professional players now.
So the algorithm is proprietary then?
We published the algorithm, and people can implement that if they like, but we didn't open source any of the code. Yeah?
As a Go player, AlphaGo has a problem from my perspective. Just when I take the leading position, it will stop playing the best moves and can empty phase.
Yeah, it's an interesting problem. So what AlphaGo is trying to do is to maximize its probability of winning. When that probability of winning is essentially at 100%, then certain moves look the same for AlphaGo. It can give away a point or two. If it's currently winning by 5 points, it doesn't care if it gives away a point or two. And that can be very frustrating for human opponents, because the moment you see basically it doesn't care anymore as long as it's... Yeah, it's an interesting problem. I'm not sure it can be solved while retaining the playing strength. That's an interesting challenge, because the criterion that we use is winning probability and not winning by a certain margin. If we now change the criterion in training from winning probability to please win by the maximum possible margin, then there might be side effects, like it might start taking certain risks now to win by a larger margin. And so what you'd be asking for is really maintain your high winning probability while at the same time maximizing the margin of winning. That would lead to those non-slack moves. And yeah, it's tricky. Maybe it can be done, but I think our research was mostly driven towards the most principal question of maximize winning probability and not consider the margin. Okay, I think we need to get out of here. Thank you very much for your attention.